Okay, so now last time I promised to you that I would move ahead with the last problem, which is torsion of non-circular cross sections. But I decided to squeeze in one more problem that has to do with the area stress function. When you look at the number of problems we've solved, this sort of balances the number of problems for displacement-based and stress-based solutions. So this is why I'm introducing this additional problem. And it's also a problem that falls sort of within my interests. And I am picking a ambitious name for it towards contact mechanics. I'm picking this name because hopefully by the end of this lecture I will demonstrate to you why the problem that we are about to solve is something that taking us towards contact mechanics. It's the first step that you typically have to take care of when you want to deal with so-called contact mechanics problems. And I will also try to tell you what that means towards the end of the course. So the problem that I'm about to solve is actually conceptually quite simple. We have a surface. Okay? Actually, the problem that I'm about to solve is very simple. We will have a surface, and I'm going to load that surface with a point force. Okay? The surface is going to be very broad. It's going to be very deep. And we're going to apply a normal force and also a tangential force. Okay? But we're going to apply it at a point. Okay? So now, the domain is very large, and it goes, let's say, infinitely large towards left, right, and downwards. But I'm just going to draw it like this. So it's as though we're taking a section, but it's just like it's not a real boundary. Okay? It's just I'm drawing a portion of this domain. And let me draw this a little bit larger. Okay. So this is a semi-infinite, right? It's just infinite in one direction, semi-infinite. I'm going to call it a plate. So again, as usual, we're going to solve this problem in a unified setting where we might have plane stress or plane strain, although this problem eventually is more natural to think of in terms of plane strain than stress, because if it's plane stress, then it means I'm looking at a very wide and very deep object that is also very thin. And if you try to load such an object with a point force, what will happen is we will just buckle. Okay, so that's not quite a natural thing to do. We want to have the object very broad, and I want to impose a point force. Now, let me actually correct one thing that I did not quite say correctly. It's not going to be a point force because that would be a three-dimensional problem. So I'm going to put a line force. But when you look from the front, what you will see is that it's like a 2D problem, and you're just going to see force per unit length. Okay, so when I draw this problem, it's a line force, and that force is going in the vertical direction. And let's call it N, and also in the horizontal direction. And I'm assuming that that force is applied at a point per unit length. Okay, so this is load per unit length. Or let's say per unit thickness. So the forces are in Newton per meter. And just to get thickness out of the way, I'm going to assume that the thickness is 1. Okay? So I'm going to assume unit thickness because eventually I have to do an equilibrium of forces, and when I integrate the forces, the net force has to be n times, because this is per unit thickness, times the thickness. I'm just going to assume that the thickness is 1 so that we don't have t appearing. It's really irrelevant to our solution. So this is the point of application of the normal and tangential force. And so it is natural that we pick our coordinate system, x1 and x2, to align somehow with that point. Okay? So additionally, it turns out because of the setup of the problem, well, it turns out it's more natural to solve it, and you will see why. It's more natural to solve it in a cylindrical coordinate system. So that will eventually be the radial position, and the angle is as usual with respect to x1. So if I look at any point in a radial a cylindrical coordinate system, there will be two stresses here. There will be a sigma RR, and there will be a sigma on the plane with normal r in the direction theta, sigma r theta. Eventually, there is, of course, also a sigma theta theta, but I'm indicating these explicitly because shortly we will make use of it. So the conditions are that there is no body force and there is no acceleration. The only thing that we have is this point force on the semi-infinite plate of unit thickness. So again, our solution will eventually hold for plane stress or plane stress, but let's imagine that eventually, in practice, we're aiming more for a plane strain type of condition. So in cylindrical coordinates, I have to remind you, or write, in fact, in the course for the first time, how the stresses are computed from an area stress function, because that will be the approach that we are going to pursue. Remember, F is equal to 0, which means that omega, right? It's the potential from which the body force comes. Omega is equal to 0. So when I write the expression in this particular problem for the stresses and for everything else that we are trying to calculate, remember, there is an omega appearing that we have used before in Cartesian coordinates. In the present case, because omega is 0, I'm writing the expressions that are particular to that case. Okay? So if it were there, there would be additional terms. But in the present case, so for instance, for stresses, we will use sigma RR is 1 del R del phi over del R, where phi is the area stress function, plus 1 over R squared del square phi del theta square. And then we have the theta theta component. Okay, and sigma R theta component. This is, for the time being, what I need. And eventually, we will need compatibility. Eventually, we will solve for displacements. But these are to be discussed. Okay. And in those expressions as well, because omega is 0, I'm going to write the specialized expressions for those cases. Okay, so to complete sort of the setup of the problem, I will also write down the boundary conditions. So these are all physical boundary conditions, right? So let me state those. So this is the physical in the sense that it's already present in the problem. I'm not relaxing anything. I'm not modifying it. This is the way the boundary conditions appear. And there are two types of boundary conditions. We have encountered these before. We will have eventually pointwise and integral type of boundary conditions. The pointwise boundary conditions simply have to do with the fact that the top surface, the surface where I'm loading, is traction-free. Okay? So I'm not applying anything here. I'm not applying anything there. So we have to make that remark a little bit carefully, because at the point of application of the force, right, it's a strange situation. I am doing something to the surface, but if I omit the point r equals 0, which is this blue point, if I omit that point alone, everything else is traction free. So that's what I'm going to write here. So sigma r theta is equal to sigma theta theta. It's equal to 0. And that holds at theta plus or minus pi over 2, right? So for any value of r, except for r is not equal to 0. So theta equals plus pi over 2 takes us to the right of the blue point, minus pi over 2 takes us to the left of the blue point. So those surfaces are traction free. And then we have the integral conditions, which is really static equilibrium. Okay, so let me just highlight a few things here. So I'm enforcing physical boundary conditions. Notice that eventually I'm going to only talk about boundary conditions on stress. Point-wise I've done. Integral I'll do shortly. There is, in this problem, no visible boundary condition on displacement. I'm not fixing any point, right? I'm not prescribing any displacement. You don't really see any condition on displacement in this problem. So we're going to see how that comes into play much later when I try to do a comparison with the numerical solution. OK, so for static equilibrium, what I'm going to do is I've drawn already that dotted circular line, right? So let's imagine we look at the free body diagram of this semicircle, or this disk, right? I apply a force at the top, and there are sigma rr and sigma r theta stresses that are forming on the surface. The stress distribution here must integrate to n and v in the normal and tangential directions. So that's essentially what I'm going to write. So first, if I sum must integrate to minus those quantities for it to be in equilibrium. So first, I'll do an equilibrium in the vertical direction. So sigma rr has a component cosine theta. And then there's a sigma r theta. It's going to be a sine theta, and it's going to be a minus. And integral dA. So that's should be equal to minus. And likewise, if I integrate minus pi over 2 to pi over 2, so I'm integrating on the dotted semicircle, the horizontal components, which is sigma rr sine theta plus sigma r theta cosine theta dA, that should be equal to minus v. So we have equilibrium. Okay, so I'm going to call this equation number 1. I will refer to it soon. And the second one, condition number 2. Okay, so one thing I'd like to highlight here now, which is important for us to think about the area stress function, let's look at the area of integration, dA. So I'm integrating on the dotted line. So it is the thickness, which I already took to be 1. Okay, so there is a unit thickness, but I'm omitting it, right, to simplify things. And then r d theta is the area. So the area is equal to r d theta with unit thickness. Okay, so that's the setup of the problem. Now remember, since we are in the stress-based approach, in the displacement-based approach, we were also doing the same thing. The first step is to construct a problem-tailored form of whatever are solution variables. In this case, it's the area stress function. So for that, I have to construct a problem-tailored form. And that construction is going to be based crucially on this simple observation that dA is simply r d theta. So let's do this. Now, in this problem, there are several ways to go about and reason why phi is about to take the form that I am going to propose, but I'm going to take the more pragmatic approach and fall back to an argument that I had done at the very beginning of the course when we were looking at the torsion of a circular cylinder. There we had a function that was a function of multiple variables, multiple coordinates. And I told you that the physicist's first line of attack would be a separation of variables. So that's what I'm going to propose presently as well. So let's pursue a separation of variables approach. Now, I don't know if that will take me anywhere. Well, I know presently that it will take me somewhere, but in general, you wouldn't know, right? So what you just try the simplest thing possible, and then you see if you can satisfy all the boundary conditions and the differential equations for equilibrium, etc. And if you can, then this is a solution. And the nice thing about linear elasticity is there is uniqueness. So if you find a solution, and it satisfies everything, then it must be the solution. Okay, so we are proposing a separation of variables, and if it works, it must be the solution, and in this case as well, it is. So I'm going to propose that phi is a function of r alone, zeta of r, times a function of theta alone, eta of theta. Okay, now if you've written that, let me pull up this board. Okay. Now, the second argument specifies the particular form of the function zeta of r, okay, in phi. And you look at the integral and the right-hand side. The right-hand side is a constant in all cases, right? And this integral represents the force on this, on the red surface, on the dotted red surface of the semicircular disk. But this disk could be arbitrarily large. I could have taken this cut here, there, or even further, right? So no matter how large that cut is, this equality holds. Now, the area of integration is scaling with r, and therefore, unless the stresses scale with 1 over r, there is no way that I can match a constant. Does that argument make sense? Right? This is scaling with r. The right-hand side is a constant. For this integral to be equal to a constant, stresses must scale with 1 over r. And that's going to be my argument. Now, so for instance, let's have a look at sigma rr. And let's momentarily forget about that term. So sigma rr must scale with 1 over r. There already is a 1 over r. And therefore, this term must be a constant. In other words, the r dependence of phi must be linear. Right? 1 over r, it's already here, so this must be a constant. That's the argument that we're going to make. Okay? So let's make a note of it. So dA is proportional to r, and I'm sorry, just going to pull up star just for you as a reference by observing the relation between stress and the area stress function. That's what I've called star. So by observing the area And if you look at the form of the stress, then you conclude that the stresses must scale with 1 over r. So of course, here there is the underlying assumption that I can take this boundary really anywhere, as far as I want. Okay? So that is the underlying assumption of a semi-infinite plane. Okay? So it's not a finite domain. I can take it arbitrarily far away, and that's how I make the argument that sigma must scale with 1 over r. And therefore, there is this underlying assumption of infinite domain or semi-infinite domain within this argument. So, and I've already told you that for that to be the case, phi must be linear in R, and that means that zeta must be linear in R. We're just going to pick zeta to be equal to R. There could be some multiplicative constant or additive constant, whatever. I'm throwing all of that into, well, there couldn't be a additive constant, but there could be a multiplicative constant, and I'm throwing all of that into eta. Okay, so we are actually in good shape already. So we're going to say that phi is equal to r eta of theta. Okay. So separation of variables plus a simple observation regarding static equilibrium. I have not enforced the boundary condition yet. I've just looked at the form of the integral boundary condition, and I made this observation. Okay, so now this form will take us far, in fact, all the way to the solution. So you will remember that in general, there is no particular well-defined order into proceeding now with the problem once we had the problem-tailored form. I could either make use of the boundary conditions partially, which I have always done before, or I could make use of compatibility. In this case, I'm going to directly make use of compatibility, and it turns out that condition will immediately deliver us a general form for eta as a function of theta. In that form, there will be some constants, which I will then determine with boundary conditions. Okay? So first, let's proceed with compatibility. Okay, so the compatibility, it's the twice Laplacian of phi, and it's equal to 0. In this particular problem where there is no body force. Let me remind you, although you have partially made use of these in your exams and midterms, homeworks, the Laplacian in cylindrical coordinates, it's as follows. So I'm going to enforce that. So let's proceed. So presently we have r eta of theta. So if you plug that in, let's first evaluate the Laplacian. Now, one thing you may want to notice at this stage, just eventually it might make our life a little bit easier in the future so that we don't have to reevaluate some terms again and again. I'm going to pull up this board and have a look at the form of the Laplacian. Twice r squared derivative, r derivative, 1 over r del del r, 1 over r squared del. So if you look at those terms, the first derivative, it's here, and the second two, the second and the third ones, they are here. So if you may want to notice that this term is, and I'll write it in parentheses presently, sigma theta theta plus sigma RR. Okay. Just as a future reference, I will remind you once again. So Now, presently, the derivative is quite simple. This derivative vanishes. The second derivative gives us a 1 over r eta. And the last derivative gives us a 1 over r eta double prime. Okay. So the Laplacian of phi is that quantity. So now I need to take the Laplacian once again. So I need to apply that operation one more time. So let me do it step by step. So you can first take the first term, right? Minus 1 over r squared, and then once again, 2 over r cubed. So 2 over r cubed, eta plus eta double prime, plus or minus 1 over r cubed, eta plus eta double prime, and then plus 1 over r cubed, eta double prime plus eta fourth derivative. And then you can collect terms. And this, of course, has to be equal to 0. That's the condition of compatibility. So if you multiply, get rid of the r cubed term, and then collect terms of equal derivatives. So we have eta to the fourth, eta fourth derivative. And then we have a second derivative, 1. This cancels, plus 2, eta double prime. And then 2 minus 1, and that's it. That's the requirement of compatibility. Okay, so back to your first ODE course, partial differential course. So it's linear, ordinary differential equation, homogeneous. And so you would go ahead and, so I'm just recording for your reference. You proceed with the proposal e to the m theta. You get your characteristic function, m to the power 4 plus 2m squared plus m is equal to 0, right? And that's equal to m squared plus 1 squared. So you have, first of all, because of the square repeated roots, and m squared delivers plus minus identity. Okay? So let's write over here. We have repeated roots plus minus I. Instead of working with exponentials, you express them as sine and cosine. Okay? And because of the fact that these roots are repeated, remember what you have to do is you have to throw in the variable of dependence into the constant. Okay? They're repeated once, so there's going to be some linear dependence. So in other words, I'm going to propose that the solution is of the form. So it's repeated. Eta is equal to, let me pick the constants to be A and B. Repetition, so I'm going to throw in a theta in there, sine theta, plus C plus D theta, cosine theta. Okay. So that is the form of the function eta. So I now have the form, general form, a problem-tailored form for the area stress function. I need to determine the constants that are appearing in that solution. And we're going to do that by looking at the boundary conditions. The boundary conditions are in terms of stress, so we need to first look at the stress. So we have phi equals eta r, and eta is equal to so Now, the simple part is, actually, I could have already written this before, and I'm going to pull up the board quickly here. So if you look here now, eta is r, sorry, phi is r eta. Second derivative with respect to r vanishes. And you take 1 over r. This is independent of r. One more derivative, it vanishes. So sigma r theta and theta theta are 0 from the outset. Okay, I don't have to worry about them. And now, if you look at the remark that I made before, I have to evaluate sigma rr. Theta theta is already 0, so sigma rr is Laplacian phi, which is equal to that quantity. So it's already evaluated. I'm just going to write it over again. So sigma r theta is equal to sigma theta theta is equal to 0 everywhere. Now, you might be skeptical at this stage whether that makes sense or not, but eventually, again, I will compare with the numerical solution, and you will see indeed it is so. And moreover, now when you look at the boundary conditions, we had two types of boundary conditions, pointwise and integral, and the pointwise boundary condition said that the top surface was traction-free, which required that there sigma r theta and theta theta is equal to 0. Well, they are identically satisfied because they're 0 not only there, but actually everywhere. So I don't have to worry about the pointwise boundary conditions. So now let's have a look at sigma rr. Okay. So sigma rr, I already told you. You can go ahead and evaluate, but it's in this case equal to Laplacian of phi. And I have evaluated that already. It's over there. So now what I have to do is I know the form of eta. It's up here. I need to take the second derivative. I'm going to spare you some calculation effort and immediately write that eta double prime, if you go ahead with the calculation, you will find after 2 lines that eta double prime is minus eta plus 2b cosine theta minus 2d sine theta. And therefore, when you calculate sigma rr, so when you sum these two quantities, etas cancel, you're going to be only left with that term. So sigma rr is equal to 2 over r b cosine theta minus d sine theta. Now, there's something peculiar about the solution that we have encountered before, but we always sort of omitted it or got rid of it because we said, oh, OK, for the physics to make sense, we shouldn't have any singular terms in our solution. But the physics of the problem in every case that we considered so far did not allow a singularity. In this problem, by nature, there is a singularity. The singularity is in the physics of the problem because I have a point force. Point force, right under the application of the point force, I have an infinitesimal area, let's say approaching 0. Force over area is going to be an infinite stress. Right? So the singularity must be present, and I will have to deal with it. So I'm not omitting anything. So there is nothing to sort of sweep under the rug. Singularity is in the physics of the problem. Now, of course, it's in the physics of the problem to within the limits of my overall formulation of the problem, which relies on linear elasticity, right? So in the natural world, if you have such a high stress near a certain region, as R goes to 0, the material will either break or yield, etc. But in my theoretical world, I'm not allowing that, and therefore the stresses are allowed to rise up to infinity. Okay? So that's the form of the stress. And now let's go ahead and determine what these constants B and D are. So I have two constants, and I have, let me pull this board up. I have two conditions on the stress. So I'll carry over this term to this board, which I'm about to erase. I think so, yes. So let's invoke the boundary conditions. So we have only integral boundary conditions remaining. And we're going to make use of those. So the first one. Okay. So we have the first one is equivalent to minus n equals, right? If you look at those expressions, my life simplified a little bit because I found out that sigma r theta is equal to 0. So that term and that term dies. I only have to deal with the sigma rr terms. Okay, so let's come over here. So for n, we have minus pi over 2 to pi over 2, sigma rr cosine theta, and dA r d theta. And if I plug in sigma rr from the expression that we have just developed, so here I'm doing nothing but plugging in the form for sigma r. Okay. That's the integral. And I have suggestively collected some terms over here for your convenience. So the 2 cosine squared theta term, I'm just writing these. I'm sure you could do these on your own, but as you try to review or develop the solution, fill up the details. Just to guide you, the first term is 1 plus cosine 2 theta. The second one is sine 2 theta. And you will observe that, therefore, theta goes from minus pi over 2 to pi over 2. The second term is an odd term. It will vanish. The first one is even. It will survive. Okay? So this one is going to disappear. And you can easily integrate cosine 2 theta. So it's b. There's a constant. So I'm going to have a theta plus 1/2 sine 2 theta. Okay? Integral minus pi over 2 to pi over 2. Okay. Now, moreover, due to the limits of the integral, so pi over 2 theta, sine term again vanishes when I evaluate. I'm only going to be left with the theta term, so it's simply b times pi. So as complicated as it might seem, the result is quite straightforward. So therefore, now, minus n is equal to b pi. So b is equal to, or let's write this in red. B is equal to minus n over pi. So that's our first finding. Let me go ahead and squeeze in the second expression here. So the second one says that minus v is equal to, again, minus pi over 2 to pi over 2. This time, sigma rr sine theta r d theta. And again, I'm going to go ahead and plug in the expression for sigma rr. So it's b to sine theta cosine theta. let me note again that there was an R term, but it was also in sigma RR, so it canceled, right? So this now is going to be also simplified. And so we have the first term, it's sine 2 theta, and the second one is 1 minus cosine 2 theta. And the first one, again, it's odd. The second one, it's even. This one is going to cancel from the outset, right? And so the answer is minus d theta, and then minus sine 1/2 2 theta minus pi over 2 to pi over 2. And that's simply minus d pi. And therefore, minus d pi is equal to minus v, and therefore we find that d is equal to v over pi. Okay, so as a result, sigma RR is equal to, let me not squeeze it. Well, let me do squeeze it in there so that we have everything on one board, just with a different color. Sigma RR was equal to 2 over R, right? B cosine theta minus D sine theta. B cosine theta minus d sine theta. So the minus I will take outside. And there is a common pi here. I'm also going to take that outside. Okay? And b cosine theta multiplies n plus v sine theta. Okay? So that's the expression for our stress. And now when you look at the stress and remember the setup of the problem, right? This is x1 coordinate. This is the x2 coordinate. And this is the angle theta at a position r. Okay? So when theta is positive, it takes us ahead of the point of application of the forces, normal and tangential. When it is negative, it takes us behind the point of application of the forces. So now the problem, of course, it's a linear problem. I could have looked at two problems. Could have looked at the problem where there is an only n or where there is an only v. Okay? So, and then I could superpose the two solutions. The superposed solution is the problem that I have solved. But if you look individually, if v is equal to 0, that would be the solution with the normal force alone. That would be the solution with the tangential force alone, right? So now when I look at those problems individually, you notice that there is a minus sign. And cosine theta, it's always positive from minus pi over 2 to pi over 2. So with respect to sigma RR, the normal force causes always compression, which makes sense because I'm pushing on the domain in the vertical direction. Now, when you look at the tangential force loading on the other hand, right, sine theta is positive ahead of the point of application of the force and it's negative behind. So when I move ahead of the point of application of the force, I'm pushing this point to the right. I expect compression in this region, right? And indeed, I get compression. And behind, I'm sort of pulling on the material that is lagging behind the point of application of the force. Minus minus makes a plus, so it gives me a tensile force. So no matter what you do in this setup, in this quadrant, you're going to have a compressive force, a compressive stress. But in this case, depending on the relative magnitudes of N and V, it could be either compressive or tensile. Okay? So, and we're going to see that solution also numerically. So it's actually a quite elegant solution, exceedingly elegant, I think. And on the other hand, the distribution also looks simple, but when we visualize it, it is quite complicated. Okay, so we're going to have a look at that. So we do have some time remaining. So what I like to do now is essentially, so this is the plan. Of course, next I'm going to go to displacements. I'm going to solve for the displacements. And afterwards, I'm going to do a comparison with the numerical solution. But while we're at this point, let me look at the opportunities that arise from this type of a solution. What else can we do based on the fact that we have now solved this very fundamental problem? And let us just briefly discuss this. And thereby, I'd like to make or justify the topic, the title of the lecture that I have chosen. So I will call these vast opportunities. It really is so. So once you solve this problem, then you can start thinking about much more complicated problems as well. So let me first look at a problem where there is not a pointwise force, but rather a distributed load. I'm not going to solve anything more. I'm not going to be very rigorous or precise with the discussion that is about to follow. I just want to give you an idea of how the solution that we have just completed is a step towards dealing with more complicated problems. So the distributed load would be a setting that is quite similar to the setting that we have looked at. We have a domain. The domain is deformable. It has a Poisson ratio and a Young's modulus eventually that characterizes the domain. But instead of a pointwise force, I will assume that we have a distributed force. If you look at any one of those arrows, let me draw actually an extra one in red. If you just concentrate on the red arrow, that's the problem that we have solved almost, with the difference that this distribution is Newton per meter squared, and therefore the magnitude of the red arrow is infinitesimally small. Okay? Only the integral has a finite magnitude in terms of Newton per meters. Okay? So I'm drawing a normal distribution. I could have likewise drawn a tangential distribution, something like a frictional sort of application of a force. Right? Let's just concentrate on the pressure distribution. So in this case, if we look at that just single arrow, we know, in this case, the influence of every force on solution. So for every one of these forces, I could individually carry out a solution. Now, what I have to keep in mind is that those forces are infinitesimal in magnitude. Now, once you carry out a solution for every one of those forces, and actually it is sufficient to do it once, and we have actually in our solution already done it. So if I seek the solution where all of those forces, all of those arrows are simultaneously present, I use the principle of superposition, right? So I have to sum up the solution for the solution corresponding to every one of the arrows, but I have an infinitesimal set of forces. It's a distribution, so it's not a sum, but it's really an integral. So if I integrate the solution distribution, if you like, then I get the solution for this problem. It's as simple as that, actually. It doesn't require any new sort of detailed solution. You just have to be clever with the superposition and the integral, and that's all. Okay? So we could have done it. It would have taken us half an hour, but we're not going to do it. So use superposition. So in this case, you have to do integration to find the solution to this problem. Now, that is the first remark. Now, suppose you can find the stress, and eventually I'm going to solve for displacement as well for the problem that we're considering. The displacement that corresponds through superposition to a particular pressure and or a traction, tangential traction distribution, right? So that is quite a capability. So what else can we do with it? So we can next look at a problem that is a little bit peculiar. It doesn't have any well-defined pressure distribution. It is not what we are prescribing. What we are prescribing is essentially a contact condition. And let me try to summarize that. Now, this problem is, therefore, the solution of this problem is going to be based on the distributed load capability. Okay? And the particular problem that I am describing is called the Hertz problem. It's a famous problem. It's been solved a very, very long time ago. And the idea is again, you have a half space that we have considered, except that instead of prescribing some pressure distribution, you take a cylinder, the cylinder is rigid, and hence I called it a rigid indenter. I'm going to push it. It's going to indent the surface. We're going to apply a force. Okay. And I'm going to first take this rigid cylinder. I'm going to make it slightly contact the surface. And let's say its weight is negligible, so it just rests on the surface. And now I apply a force gradually. Now I will increase the force, let's say, from N1 to N2 to N3. It's increasing. Now, when the force is small, this thing will indent the surface, and a portion of the cylinder will come into contact with the elastic half space, right? So let me call this 1 to 1. So this is the region of the cylinder that is going to come into contact with this deformable body at force N1. If I increase the force, that region will increase. It will become 2 to 2. If I increase it further, the region will further increase, right? It's going to be 3. So for instance, at 3, what I expect to see sort of is perhaps something like this. The cylinder itself is not deforming. It is the space, the deformable elastic body that is deforming, right? Now, this is a strange scenario. Now, we can immediately make some observations. So, for instance, where there is contact, there is going to be some pressure distribution, okay? If I know what the pressure distribution is, I know the solution to that problem. It's very easy, okay? Now, do I know the pressure distribution? Not yet, okay? Now, I can make another observation. The pressure is non-zero only where there is contact, and it is zero where there is no contact, naturally. Where there is no contact, pressure is zero. There is a distance or a gap between the surfaces. Where there is contact, the gap between the surfaces is zero. So here the pressure is non-zero, gap is zero. Here the gap is non-zero, but the pressure is zero. Pressure times gap is always equal to zero. So that's a classical formulation of a so-called constraint problem in the context of contact mechanics. So now let me sort of summarize the observations that one needs to follow in order to solve this problem. So first of all, I observed that we have an area that is associated with contact, and this contact area is not known beforehand. It grows as and grows. Okay. The second one, the observation that I have already stated, is that due to the force, we have a pressure distribution, and the pressure distribution is statically equivalent. The one that acts on the deformable object is statically equivalent to the force that I'm applying. There could also be a tangential one. Let's just focus on P. So the pressure distribution, if I know what it is, it causes a displacement field that I could easily solve based on the capability that I already, in fact, have. So the P distribution causes a displacement field, okay, which I could solve through this superposition idea. And then, however, this displacement field is a special field. It is not any field. It is such that the displacement where there is contact conforms to the geometry of the cylindrical indented. In other words, the indented object takes the form of whatever, the elastic body takes the form of whatever object is indenting it, right? So U field must be such that it conforms to the geometry of the cylindrical indenter. And this is really where the idea of a constraint comes into place. It's not any displacement field. It's one that conforms to the geometry of the cylindrical indenter. And that's about it. So if I wanted to solve this problem, I have to put this information together and try to satisfy the constraint and thereby find the pressure and hence the displacement field that is the solution to this problem. Again, once I have solved, I've done the hard part of the work. And if I proceeded a little bit, I would be able to take into account distributed load. And once I do that, going back here and solving this problem, it's not easy, but it would take us, let's say, an hour, and we would be able to do it. Okay? And then, if you want to consider that you are pressing this object, and there is presently, I'm assuming that there is no friction. If I also want to slide it to the right in the presence of friction, it will also cause some tangential force distribution to arise due to friction. And that I also can take into account. That is not as easy as the frictionless case, but it can be done. OK, so that is the second case. Now, point force, we've done. Distributed load, we've discussed. A deformable object being indented by a non-deformable rigid one, we have discussed. And so once you are able to do all of this, the third natural step is to look at the object, the contact of two deformable objects. So not a rigid cylinder versus a deformable one, but let's say deformable cylinder with a deformable one. So this problem would be depicted, let's say, like this. There is an object, E2, nu2, and let's say it has some dimensional parameters as well, E1. E1. The radii may or may not be the same, materials may or may not be the same, and I just press them against each other with a normal force. And the solution of this problem is based on the solution to the Hertz contact problem, problem number 2. So once you solve that problem, solving this one is also a relatively small step forward. And now, once you can solve all of these, then you can start to look at problems that are of technological interest and have been of technological interest. And believe it or not, within the last 10 years, people have made some advances towards a, let me say, a more rigorous solution of the type of problem that I'm going to describe now. And this is the contact of rough surfaces. It's a hard problem, very hard problem, both numerically and theoretically. And so the problem we'd like to depict is you have two objects, right? So here I'm looking at the contact of two very, let me say, geometrically clean objects. If you want to look at the contact of two arbitrarily shaped objects, the problem is going to be harder. It's probably not going to have an analytical solution. But there are numerical methods that you can use and solve for the solution. And the solution is the solution to a problem where you have some distributed load on one object, a distributed load, let's say, on another object. Both of the objects are deformable. And as a result of these forces, they come into contact. And now you have a contact area. And on that contact area, you have, let's say, if it's frictionless, a pressure distribution that is arising. Only a pressure distribution. And now, however, suppose that those surfaces are actually microscopically not smooth. And actually, when you zoom in, what you see is that those surfaces are rough. Now, this problem is it's surprisingly closely related to the problem that just came before it. Because if you look at these two surfaces that are microscopically rough, and so they are going to come towards each other, and eventually they are going to contact each other. So macroscopically, that's the picture, but microscopically it's slightly different. So let's say when these surfaces approach each other in the normal direction, this region will come into contact with that region. Now, when the contact areas are small and the loads are small, you can approximate everything with its radius of curvature, so almost like a circle. So we can imagine, actually, that I have two cylindrical objects, almost, not exactly, but almost two cylindrical objects coming into contact with each other. Now, however, of course, this problem would be a gross simplification towards that one, because there is not going to be only a single force, that two sets of points that come into play in contact, but many other points throughout this interface might actually be contacting each other. So you have to somehow take into account all the possible combinations if you want to look at the micromechanics of this contact problem. But really, the underlying idea at one point or another goes back to the first problem that we solved. In order to say something about this problem, you have to understand something in some sense about this problem. This one is based on number 2, 2 is based on number 1, and 1 is based on the problem that we have solved. Okay? And that's why I chose a very ambitious title for the title of this lecture, because really it takes one quite far in terms of these sets of problems under the title of contact mechanics. And it is a very important set of problems. Questions?
What happens
Oh, okay. Good. So let's take a step, actually 2 steps back. What if I was not considering a line load, but a point load, right? So the starting point would be that. So first a point load, and then a distribution of forces in a certain area, not across a band, as I am intrinsically assuming here, because it's 2D, right? And then it would be a sphere, right? So then the first problem we have to solve is really a point load. And that we could have solved. Let me try to depict it clearly. Well, maybe this is a good point to depict it. So in that case, if it's like this, right, I would take a large stretch of the domain. There is a point force N. I would work in spherical coordinates. And when I try to argue about the decay of the stresses, I don't remember the details exactly, but I suppose I would argue not along the surface of a semicircular region, but rather, let's say, on the surface of maybe like something like a cone, okay? And by looking at the equilibrium, I would deduce something about the stresses, how they should decay, because the integral of those stresses should be statically equivalent to a force. I would say something about the area stress function and proceed slowly, okay? And there's a solution for that as well. Okay. Yeah. Questions? Okay, so the plan is next time I solve for the displacements, do a numerical computation, and then we'll be done with this specific problem. Okay, thank you.